So we've previously looked at how we charge a capacitor. Now let's look at how we discharge one. So imagine we have a charged capacitor. So one plate is positive and the other one is negative. Now the way you get a charged capacitor is obviously to charge it. And then if you remove that capacitor from the circuit and just leave it out, it won't lose any charge. So now let's say we connect that capacitor to a resistor or a bulb or something. Now what's going to happen is between these electrons, there's going to be a repulsive force. So accumulated electrons on the plate experience repulsive force amongst themselves. And what that means is these electrons will then start to move away from the plate. So this causes them to move away from the plate. And this is known as discharging. And as the accumulated electrons get discharged, or as they leave the plate, there's going to be less electrons on the plate, so the repulsive force decreases, and therefore the current decreases. And this basically means that the rate of discharge decreases with time. And just as a little note, these electrons do flow around the circuit and accumulate on the other plate, so you will receive a current. So graphically, what you're going to see is, as I said, it can be with either charge or voltage, as you know they are proportional, is you're going to see that this decreases with time. And actually for current as well, you'll see the exact same graph. And we have some equations to depict the discharging of capacitors. And for charge, it's Q is equal to Q naught e to the minus t over RC. For voltage is equal to V naught e to the minus t over RC. And again, as with charging, these values mean the same thing, where Q or V is your charge or voltage at the specific time. Q naught and V naught are actually your initial readings or values, so your initial charge or voltage values before the discharging takes place. T is the time after discharging starts. R is your resistance of the circuit, and C is your capacitance of the capacitor. And for current, you actually see that I is equal to I naught e to the minus t over RC, which you may realize is the exact same as the charging equation. And remember, we get this equation by differentiating the charge equation here. And the two charge and voltage equations are quite similar to those of the charging equations. But in charging, it's 1 minus this e to the minus t over RC, but in discharging, there is no 1 minus. And as for discharging, we also have this time constant concept. And your time constant is again equal to RC. But your definition in terms of discharging is that your time constant is the time taken for your capacitor to discharge to 37% of its initial value. So let's say your capacitor was initially at 100 volts and you discharged it. As you know, the graph would look something like this. After one time constant, you would see that the voltage reading across the capacitor is 37 volts. And again, you can say that after 5 time constants, the capacitor has completely discharged. Now, if they ask you for your time constant definition in the exam, you can use either the charging or discharging equation, unless the question specifically asks for one of them in particular. Also, you should notice that this 37% is equal to 100 minus 63%, and 63% was the percentage of voltage or charge reading after one time constant for a charging capacitor. Let's just do a quick bit of analysis on this equation here. Sometimes when you're plotting graphs for practicals or otherwise, you always want to try and plot a straight line graph. So what you could do here is actually take the log of both sides, the natural log, we'll call it ln. So if you do ln v or is equal to ln of v naught e to the minus t over rc. Now using some laws of maths that you may or may not have learned, we can get that this is equal to ln of v naught minus t over rc. So if you want to get a straight line graph, you could actually plot ln of v against time. So if we relate this to y equals mx plus c, we know that the y value is ln of v. You've got x as your t, and your gradient is therefore this minus 1 over rc. So your gradient of this graph is minus 1 over rc. And this graph will be a straight line with y-intercept of ln of v naught. And you may also notice that the gradient is also equal to minus 1 over the time constant. Now the best piece of advice I can give you after watching that video is to go off and practice on past papers or topic questions. These are single-handedly the best way to help you commit the content you've learned to memory. Obviously go and do all the YouTube stuff of liking, subscribing, and if you found this video helpful, feel free to go and watch any of my other ones.